and take your seats so we can get started. Good morning. I'm Bill Phillips from the Joint Quantum Institute, and it is my honor to welcome you to this 24th International Conference on Atomic Physics. My first ICAP was the third ICAP in 1972. I was a young graduate student attending my first international conference, and I was eager to meet some of the famous physicists about whom I had only heard or read. Like many of you, I was presenting a poster, and I was pleased with the interest that some of the attendees showed in it. And today, I'm quite sure that no one remembers it. And I'm pretty sure I don't remember any of the details of the talks or posters that I went to in 1972. What I do remember is the excitement of hearing about the latest developments from the people who were leading them. And I remember the people I met, the friendships and the connections I made, and the way in which those friendships and the ones that grew out of other meetings have continued to this day and have enriched my understanding of physics and my appreciation for life. As I look out on this group, I realize that I have known many of you for a long, long time. I met some of you before I was married, and I've been married for more than 44 years. Some of you I've met more recently, and I look forward to meeting some of you for the first time. Of course, at my age, it may just seem to me that I'm meeting you for the first time, and I hope that you'll forgive me for that. It's particularly moving for me to know that Guillaume Solomon is at this meeting. Guillaume, who is attending with his famous father, is someone I've known since he was a baby. I fondly remember carrying him on my shoulders in the French Alps and reading bedtime stories to him and his siblings when I would visit the Solomon family in Paris. It's a great pleasure to know that he is now among the young people attending this ICAP, much in the same way that I was 42 years ago at my first ICAP. To all the young people here, I urge you to soak up the physics and to treasure the personal connections you make at ICAP. To the older people, I urge you to be open to discussions with the young people. Those contacts meant a great deal to me so many years ago when I was so young, and they will be similarly important to the young people of today. And to emphasize how serious I am about that, I promise to have lunch with any young people who approach me, whoever asks me first. Just see me during a break, and we'll make a plan to have lunch together if you want to. As I think about the way atomic physics has developed over the years, it seems to me that it keeps getting more and more exciting. The Joint Quantum Institute, which is hosting this meeting, started just 8 years ago as a cooperative venture of the University of Maryland and the National Institute of Standards and Technology, with the support and participation of the Laboratory for Physical Sciences. For the past 6 years, we've had transformative support from the National Science Foundation in the form of a Physics Frontier Center. In this comparatively short time, the JQI has experienced an explosion of interest and progress in quantum phenomena, often at the intersection of atomic and condensed matter physics. This is going to be a recurring theme at this ICAP as it is at the JQI. In atomic physics institutions around the world, similar excitement is constantly being evolved, and I hope that many of you will take the opportunity to see firsthand some of that activity during the lab visits to the JQI on Wednesday afternoon. None of this could even have been imagined by the attendees at that 1972 ICAP, and little of it could have been imagined just 20 years ago. This is an exciting time to be an atomic physicist, and ICAP is the place to learn about the latest exciting developments from all over the world. It's particularly pleasant that we get to experience this in the historic Mayflower Hotel. The 33rd President of the United States, Harry Truman, called the Mayflower the second best address in Washington. Legendary FBI Director J. Edgar Hoover ate lunch here every day for 20 years. Franklin Roosevelt wrote his first inaugural address in 1933 on the 7th floor of this hotel. This week, you will make history of a different sort at the Mayflower. That history will consist not just of the new physics of today, but in planting the seeds for the new physics of tomorrow. This wonderful conference in this historic place has come to you through the hard work of the organizers of ICAP 2014. And the co-chairs, Gretchen Campbell and Trey Porto, are the ones who most deserve our thanks for having such a wonderful conference. And now I'd like to turn the podium over to Gretchen and Trey to tell you some of the details about the conference.
Well, I'd like to extend my welcome as well. It looks like it's going to be a nice week. For those of you who have not visited Washington, D.C. before, you have been given a treat regarding the weather. It's usually a lot hotter and a lot more humid than this. So we just wanted to give a couple of technical things. Those of you that have posters, which is all the young people that Bill wants to encourage, the poster is going to be set up in two different rooms. Where the reception was last night is where posters 65 through 164 are going to be. The poster boards are being set up as we speak. So starting, I believe, as early as the break, you can go in and put the posters in. And then the 1 through 64 will be in the room just behind this, where you can set up your posters at any time. It's important to take your posters down in time for the next people to get their posters up, so you should remove them or they will be removed for you by the break the following day. So that is going to be at 10:15 the following morning. Most importantly, the food and coffee are spread out all over the place so that you don't have to just be in the promenade. So it'll be in both poster sessions. In the mornings, when you come to get something to eat, you can spread out and go everywhere. Okay. I think Gretchen has a few things to say.
And just a few more logistics. The big thing is don't forget to pick up your ICAP mug. So when you all registered, you got a purple ticket. So starting today, you can stop by at the registration and pick up your mug whenever it's most convenient. We just didn't want you to have to carry it around with you all last night at the reception, but don't forget to pick up your mug. There is limited space still available for the Mount Vernon excursion, so there are still a few more spots available if any people have not yet signed up for that. So that excursion is on Wednesday afternoon. And there's a sign-up near the registration desk for that. Now, as Bill mentioned, there are lab tours on Wednesday afternoon. So currently the buses are full. We had a lot more demand for this than we anticipated. Now we're working to see if we can get some additional buses lined up, but in addition to buses, the JQI is actually easily accessible via public transportation, so we'll have maps available as well as JQI volunteers, which can help people get to the JQI via public transportation if you're not able to get on the bus. The way we're filling the bus is sort of a first come, first served, whereas if you signed up online, if you were one of the first people to sign up online, that will give you a spot on the bus, and then we'll have a waiting list for the bus after that. And we have somebody in the hall who will be able to tell you if you're on the bus or not. Another thing is, although we're just starting ICAP 2014, it's not too early to start thinking about 2016, and there's some very nice information about ICAP 2016 at the registration booth. So when you pick up your mug, it's also a good time to also pick up some information about the next ICAP, which will be in Seoul, Korea. So, internet. So we've already had some questions about that. If you're staying in the Mayflower, the internet in your rooms is complimentary. When you log in, you have to accept the charges, but when you check out, you will not actually be charged for it. Let us know if you have any problems with that. Now, we do not have internet access in the lecture hall. So there's internet in your rooms and in the common spaces, but there is no internet in this hall. Just some more information. So our banquet speaker, we're really happy to say, will be Davis Sobel, who is an author of a number of very nice books, Longitude, Galileo's Daughter, as well as a more recent book about Copernicus. She'll be our after-dinner speaker, and before and after the banquet, she'll be signing books, and we'll have some for sale in the lobby. And finally, if you're a student with a poster, thanks to support from a couple of journals, we're happy to announce that we actually have a student poster competition. So if you're a graduate student presenting a poster and you would like for your poster to be part of this competition, please make sure to sign up at the JQI desk. And finally, if you have any questions during the conference, feel free to ask Trey or I. Or in addition, there's a number of helpers from the JQI who you can spot. They should mostly have blue shirts on. So if you see any blue-shirted JQI people, feel free to ask them any questions. They can either answer your questions or direct you to the appropriate person who can answer them for you. And I think that's it. And with that, I'd like to welcome Bill back up here, who will be the chair for our first session this morning.
One of the indications of how exciting atomic physics has been in the last several years is the fact that people in atomic physics have been regularly getting Nobel Prizes for their work. And ICAP has regularly taken advantage of those atomic physics Nobel laureates by inviting them to talk at the ICAP that follows the year in which they've gotten their award, and this ICAP is no exception. So Dave Wineland and Serge Haroche, the recipients of the 2012 Nobel Prize in Physics for doing neat quantum stuff, are going to be the speakers at this morning's session. So let's welcome Dave Wineland.
Yeah. Okay. All right. Thanks, Bill. Well, I too would like to acknowledge Gretchen Campbell and Trey Porto for putting together this very nice meeting. And believe me, I've been in their shoes before, so I know how much work it is. And we want to thank them and also all the people helping them for this conference. So one of the themes that's become popular in the last few years, I think most of you know, is this idea of quantum computing, quantum information, and that's been one of the main topics for our group. Actually, some of you may have seen this article in Time magazine, and sort of, I think all of you are knowledgeable enough. If you read this article, you wonder if you can ever trust anything you read in the popular media again. So some of the interesting things about this article, take note, you neutral atom trappers, the coldest place on the in the universe is in Vancouver, and they get to these low temperatures of 20 millikelvin. A couple of other things. It's amazing what these quantum computers are going to do. I hadn't heard of some of this stuff before. One of the ones I especially like is this one here. I mean, I suppose I'll get some quantum computing ads from Lady Gaga or something. I don't know. So anyway, what I'm just summary to what I'll talk about. I'm going to give a little bit of history. A little bit of personal history, and then how NIST got involved in these topics. And our main topics has been spectroscopy, and then trying to do quantum limited measurements, and more recently pursuing this idea of quantum computing and quantum simulation. Of course, many examples I give are from our group, but I'll try to give some perspective on what all of us are doing. And of course, there's many good talks here and posters that'll discuss these topics. So just a little personal history. So I was a student with Norman Ramsey. That's Norman there. That's me trying to get close to the boss there. You see. Anyway, I joined the group not long after Norman and his close colleague Dan Kleppner had invented the hydrogen maser. By the way, Dan is here at this meeting. So as part of this, continuing this work, Norman wanted to have accurate measurements of all the hydrogen isotopes. So my project was to measure the deuterium hyperfine frequency, and it was a very similar thing to the device, the way the hydrogen maser worked, but it was made a little more complicated because it's rather long wavelength. But anyway, so my thesis topic was to make this measurement of the hyperfine frequency, which you see on the left there. I've given this showed this slide before and told people I think I'm the only one in the universe that has memorized that number. But since then I've gotten a few emails from young kids who say they've memorized it now too. Anyway, I think at this, when I started this work, I was hooked after this on these kind of precision measurements, and I've always liked the detective work that goes into figuring out, of course, what the systematic shifts are and so on. And actually, in the masers, of course, we're even in these early experiments, we're dealing with rather long-lived superposition states, which occupies a lot of the work of people here at this conference. After my graduate work, I went to work as a postdoc in Hans Demont's lab. I was stimulated to go there because Hans had done some really nice precision measurements on helium, but at that time he focused on his work to measure the magnetic moment of the electron. And so one of my main projects was that it became clear not long after I was there that the most precise measurements could be done with single electrons in these things. So we needed a way to isolate single electrons. And basically what we did is if we had electrons in there, you can think of them as being harmonically bound, and they form an equivalent circuit. So if you put this equivalent circuit into a simple voltage divider, you can read out, if you drive the electron near resonance, you can get a signal out which is proportional to the number. So to get down to single electrons, basically what we did is just drive them hard enough so that occasionally they'd hit an electron and be lost. And of course, the interesting case was when he got down to this final step. So this was just a precursor to their later experiments on measuring the magnetic moment of the electron. And this was really the first high precision measurement on single electrons. And of course, Jerry Gabrielson, his colleagues have gone on to measure with even higher and higher precision. So anyway, so after my postdoc position with Hans Demont, I had hoped to go into academia, but in fact, the few offers that I got, they were the amount of research money was so small that it would have been impossible to really do anything realistic. So I went to, at that time, in around 1975, there was a position opening then the National Bureau of Standards in the time and frequency division. And when I arrived, the NIST didn't have an operating cesium clock, so there was a lot of pressure to get the clock that had been built by my colleague David Glaze to get it operational. So about a little over first year or year and a half, I was focused on that to get the device running. But nevertheless, at that time, my group leader, I should say the group at that time was other than the cesium clock, was fairly applied. We did calibrations and so on, but there was really very little research. But my group leader at that time, Helmut Helvig, was able to get some money for us to pursue this idea of laser cooling, and so we were able to set up an experiment on that. Now, so to cut to the chase, after setting this experiment up, we were trying to do a very simple demonstration. This was just Doppler cooling, very crude experiment by today's standards. But one thing that was interesting is I knew that Hans had taken a sabbatical to go work with Peter Toshak, so I knew they were working on it. I had no idea where they were in terms of progress on the experiment. I'm almost certain they didn't know about our experiment. You notice the experiments, or the results were published about the same time. Ours was a little earlier than theirs, but interestingly, you notice the submission dates here. So if you look carefully, you could say they beat us by 1 day in terms of getting this result. So anyway, this was our group not long of that. This was the entire group at that time. And one thing that's been nice for me is I basically worked with these guys all the way through our careers together. And one embarrassing thing or annoying thing is when you get old, you can see what happens. Jim Berquist and Wayne Otano, they pretty much look the same, but these other guys, I don't think you'll be able to tell. So I know a lot of water under the bridge here. It became also clear, just as for electrons, that at least we could reduce the systematic effects best if we went down to single ions. So there was a push to do experiments with single ions, and so we did a number of experiments on this. One of my favorites was this one on, we'd put a single mercury ion in a Paul trap, and we were employing this idea of Hans Stamos, which he called electron shelving amplifier, which is sort of ubiquitous in a lot of atomic experiments. The form it took here was that we would drive this optical transition. Actually, we did a lot of work on the hyperfine structure of mercury too. But in this to measure optical transitions, the idea is very simple. If you start the atom in the ground state, if you excite the transition and the atom makes it up to the upper level, when you turn on this laser here, on this strong transition, which can be used also for Doppler cooling, you see the absence of fluorescence when the ion moves up there. So it was essentially give us 100% detection efficiency. So this was a kind of spectra we measured. So some of the features of this spectrum is that the central line, this is, you might say, sort of the optical manifestation of the Mossbauer effect. It's not, of course, it's not really recoilless, but all the recoil from the photon absorption goes into the apparatus rather than just the atom itself. So the overall envelope of these lines is basically the Doppler profile close to the Doppler limit temperature. And of course, these upper and lower side bands represent the case where you make transitions on this optical transition, but in the lower side band, of course, is when you make the transition and also reduce the motional quantum number by 1. And this provided a way for us to do the cooling. We actually sped up the transition by pumping out of this level, but nevertheless, we could, by just sitting on this lower sideband, then we could get down to very near the ground state of the motion in these experiments. So anyway, we started these experiments. We actually had in 81, and we had in mind, as I say, we did a lot of work on the hyperfine structure, but we also had this in our minds for a long time. And of course, the goal was to try to do better than cesium. Of course, cesium was a moving target, but finally, this work, which was really led by Jim Berquist, finally caught up with cesium. So this was the first measurement of a transition where the systematics were below the current value of the cesium, and in some ways, I think, started the switch to, at least for high precision and accuracy, this focus nowadays on optical transitions. There's a lot of other transitions or ions people are considering. I mentioned these 2 articles here. There's one that should be coming out soon, a review article if you want to find out more about that. One of the interesting ions is thorium, and actually here it's a nuclear transition, which is of interest. And actually there's several posters on this, if you look, I think in Wednesday. But Eckhard Pike, who is also giving a presentation, I don't mark it here, I think it's on Friday or Thursday, anyway, later in the week, he's gonna also be talking about this this case here. So anyway, when this idea of quantum information, at the 1994 ICAP, which was held in Boulder, on the suggestion of actually Dan Kleppner, as a sort of a breadth talk for us, he suggested that Arthur Eckert, who was an expert in quantum communication and so on, that he suggested we invite him to give a talk and introduce us to this idea of quantum computing, and he did that. So in the audience were these guys here, which I think you all know, and of course the strength, one of the strengths of both Ignacio and Peter is that they in addition to being excellent theorists, they also keep close eye on what experiments can do, and they were the ones that really, the first to really suggest how you might, in a comprehensive way, how you might make a quantum computer. So their idea was if you have an ion trap here, in such an arrangement that the ions line up in a string, and the basic idea was that in their proposal was that you would first using laser cooling, put all the modes of motion in the ground state. And then the basic scheme is that if you have a way to, say, map the superposition of this qubit onto the motional state superposition of the ground and first excited state, you transfer the information into that qubit of the motion. And the nice thing about that is that the motion of that qubit is shared with all the ions. So if you then applied another laser which could somehow do a gate between this motional qubit and the internal state of that qubit, then you've basically done a quantum gate between those two selected qubits. And the idea here is pretty simple. If you have, for the case of optical transitions, this would be the initial state of this would be in some superposition, and then basically what's done is you just drive a red sideband transition on that, and you can transfer the amplitude of this level into this level. So that's that first mapping step. Many of us are using, rather than using optical transitions, they're using hyperfine levels for the qubits, and there's pluses and minuses on both sides. The reason a lot of same for that, of course, you can get very long coherence times with hyperfine qubits. And anyway, when we drive these pulses, this is the basic source of entanglement in these experiments, where during this transfer pulse, for example, the ions are in some entangled superposition between this motional mode, in this case, and the internal state. And of course, there's a lot of, this was where there was a lot of overlap with the work of the ion experiments with what Serge Haroche and his colleagues are doing. In this particular example, we relied on essentially the Jaynes-Cummings Hamiltonian to invoke this dynamics. And so one thing nice for me is that I followed Serge's work for a very long time, but in some sense we would always write down or many times write down the same Hamiltonian, but our experiments were different enough. We didn't really have to compete. I think it was more complementary. So it's been nice over the years to follow his work and discuss these kind of things with him. So anyway, just going on to the spin motion gate, if after we've done this mapping, then this qubit over here will in general be in this superposition state, which involves the motional mode. And then in this proposal by Ignacio and Peter, the way you make a quantum gate is that you, or one way is to drive this transition, do a 2-pi pulse on this particular transition, which puts a minus sign in front of that component of the wave function, and this is some form of phase gate or an entangling operation. And we were lucky to just be in the right place at the right time. That Chris and I had been trying to set up experiments that were exploring these ideas, and when they made their proposal, we could relatively quickly make the demonstration of this sort of the quantum gate that was central to their proposal. And later, Rainer Blott's group did the more complete form of the gate proposed by Sirac and Zoller. These days we do a little bit different, and I'll say a little bit about that now. But before I do, let me say I think this proposal by Ignacio and Peter was really extremely important for ion traps. We always had our clocks to think about and pursue, but this really changed things and stimulated a very large number of groups to pursue the ideas of this quantum information processing. So this was really important for many groups, as you see, and I unfortunately probably missed some groups. There are so many starting up all the time. Anyway, just to give you an idea, a little different perspective on how we might do these gates is that suppose, I apologize, I'm switching notation here. So these are meant to represent the internal basis states of our qubits. And the basic idea here is there's different ways to look at this gate, but one way to think about it is if we can engineer state-dependent optical dipole forces, then suppose we have a standing wave that runs transverse to the axis of our trap, and if these, if the optical dipole forces from the standing wave act on the two states differently, then, for example, the 0-0 state, those qubits might be pushed down. The upper state might be pushed up, and of course, when they're in opposites internal states, then they get pushed in difference interaction. And so, one thing you can imagine here is obviously the Coulomb interaction is different for these cases where the qubits are in opposite states. And so, for example, you may pick up some overall phase, but there's a differential phase that acts on these states with different spin, and that can make a phase gate. And of course, if you adjust the interaction time appropriately, you can get a gate that looks like that. And there's actually ways to amplify this kind of effect. Usually what we do is we drive near a motional resonance, which is easier to excite the motion than to get this difference. And there's been a number of experiments done on this. This last one I mentioned is by the Oxford group of David Lucas. This now kind of sets the world's standard for gate fidelity. They report the smallest errors on these 2-qubit gates, which is the hard part, as opposed to single-bit operations, and it's around about 1/10% now. And also, if you look at this Hamiltonian, or the Hamiltonian that governs, that gives rise to this gate interaction, it basically mimics spin-spin interactions. And that's become interesting with this idea of trying to do simulations. And a model problem that many groups, including neutral atoms and other implementations of quantum computing, are working on is as a test case to try to simulate this transverse Ising model. So based on these proposals by Porras and Sirac and other people, just to give an example of how this goes, is that suppose we have again a string of ions, but then we say use a moving standing wave to excite the motion of these ions in a state-dependent way. This case of 9 ions, there'll be a spectrum of these transverse modes of oscillation. For example, the highest frequency mode is where the ions all move together. The next lower one is where there's a tilt of this ion string, and so on down the line. Anyways, the key part is that if we tune very near the center of mass mode, and where it's dominantly excited, then we can realize a global interaction like this. For example, this is used to make GHZ states in these experiments. But also, if we change this tuning here, You can also change the effective range of the interactions, and so you can go from this global interaction basically up to a nearest neighbor dipole interaction. And this has been seen in these experiments up here. And in fact, I won't say much more about this. There's one of the very recent results that just came out a couple of weeks ago in Nature by both Chris Monroe's group and the work of Rainer Blatt and Christian Ruths in Innsbruck. We're able to create entanglement and then watch the dynamics of the entanglement propagating through these linear chains. So there's an oral presentation on this by Phil Riescherm on Friday, and there's also posters from the Innsbruck group on this work that you can look at later in the meeting. So anyways, I wanted to say a little bit about what we're doing more recently. Actually, one thing that happened in the last year, we moved to our new lab, and of course there's always delays involved with that, and the air conditioning doesn't work, of course, but things are finally coming together and the labs are getting set up. So one thing on this business of simulation we're pursuing, John Bollinger leads the effort on using ions in a pinning trap. Here he's got, the picture you have here is it's an array of ions in a 2D plane, and the motion that's of interest to realize these simulations is the motion out of the board there, and so some of the modes, this is the center mass mode, all ions oscillating back and forth out of the frame of the picture there, and then the first lower modes are tilt modes and so on, very similar to the linear chains. So in these experiments so far, they haven't seen entanglement yet, but they've characterized these interactions and the range of the interactions versus the detuning from these resonances. And if you'd like to, one of the things is that John and his guys have set up a new experiment where they've changed the laser beam geometry to increase the couplings relative to spontaneous emission, and so they're trying to get going on that. And if you'd like to find out more about that, there's this poster on Tuesday. So one other extension of that's a 2D system, which gives more variety. And so one thing that might be possible that D.D. Leibfried and others have been thinking about is to maybe through the geometry of the traps construct particular kinds of interactions. And so this is kind of the vision here to make different lattice structures by constructing the geometry of the electrodes, so you can make essentially arbitrary geometries. Now the trick here is, of course, that this shows this is meant to be a cartoon of a planar electrode structure, and the technical problems are very easy to say. Well, let me first say, so we've done sort of the first baby step in this direction. We've done in this picture here shows an apparatus, a planar structure where it's not obvious from this picture, but we have a double well structure, so each ion here is held in a separate well, and we can begin to make gates or implement this spin-spin interaction in these experiments at these distances right now of about separation of about 30 microns, and the couplings aren't great. Actually, Andrew Wilson will speak about, he's got a poster on this. But anyway, we hope we're getting into this regime where we can hopefully build devices like this. Now, of course, we would like to increase the coupling as much as we can. That means we have to make smaller traps. But everybody in the ion business knows when we try to go smaller, we see some heating, which we don't really understand yet, but it goes even a stronger scaling with distance. So we've got to reduce this heating. We've been bothered because of these UV beams and the long beam paths, we've been bothered by the quality and the spatial beam fluctuations of the intensity due to fluctuations of the beams. And so we need to attack that. And also, of course, one nice thing is maybe we can get rid of lasers, and I'll say a little bit about each one of these things here. So one of the things we've done is I mean, I must say we wish the heating would go away, but it's persisted all through our experiments, and I think it's fairly ubiquitous in the ion experiments. We see some heating. It's pretty clear it's coming from the sources, the surfaces of these ion electrodes, ion trap electrodes. So basically we started to get serious a couple of years ago, and one thing we started doing, we tried was just using a technique that's common in surface science studies to get a clean surface is that you need to clean the stuff off of the surface. And so one way to do that is to use, in this case, argon ion beam, which sputters the stuff on the surface off. And actually, we got a nice, felt like we got a nice result here. In these first experiments, we could reduce the heating we saw in this particular planar ion trap, which you see on the horizontal across the surface of the trap here. And we still don't know what we're doing, and so we're trying to figure this out. I must say, I want to mention too that Hartmut Hefner's group at Berkeley is also pursuing these same ideas and saw a similar game using this ion beam cleaning. And of course, cooling helps too. Chris Monroe's group was the first to show that they only got down to about 150 Kelvin, but they showed that the heating went down much faster than the temperature, which indicated maybe whatever's going on the surface, you're freezing it out. And there's been a lot of nice experiments done by Ike Chuang's group and more recently by John Cheverini at Lincoln Lab. So it would be nice to incorporate the ion beam cleaning with low temperature, but these apparatuses, the guns that make the ion beams are not very compatible with small compact cryo systems. So we and others are trying to do investigating laser ablation, and also it'd be nice to maybe we could just light a plasma on top of this. So there's other possibilities that might make this cleaning compatible with a low temperature apparatus. Anyway, and I think, as I say, we don't really know what's going on, so a more general attack, we got some of our colleagues in Boulder that are real professional surface scientists got interested in this problem. So the kind of thing we're pursuing now, a few years back we made a trap we called the stylus. So, in some limiting view of this thing, an ion is held at the tip of this special ion trap. And then so the idea here is that we've started to do is that we have, everything is under vacuum, and we have, say, some surface we want to test over here on the left, and we might do some sputter cleaning or deposition and so on. And then the idea is to move that test plate into the ion and measure the heating. Now, of course, the obvious thing is we have to bootstrap our way along because we're going to get some heating from the ion trap electrodes. But anyway, we started to do this and done some crude experiments so far along these lines. Also, I just also want to acknowledge again, Hartmut Hefner's group is also taking a general attack on this problem, and are doing similar experiments, and you can find out about that in this poster. So anyway, one of these annoying things, and we always looked with envy on people working in the visible part of the spectrum, because you can get fibers and very nice beams. And we'd tried this for the last 20 years to find fibers that might work. And what happens is that typically the fibers form color centers from the UV, and so they stop transmitting right away. Anyway, since I'm starting to run close on time, I won't say a lot about this, except there's kind of a magic recipe we found. And that is what this work, which was led by Yves Coulomb, was we would put these fibers in 100 atmospheres of hydrogen for about a week, and then we would just transmit the UV through the fibers. And what apparently happens is that they still form color centers, but via the hydrogen, which in some sense acts as a catalyst, they make color centers which are somewhere in the spectrum where they don't absorb. So we were actually able to get get, first of all, the nice beam quality using fibers. And in this next view graph, you see there's a lot of noise here. Basically, we just ran UV through a fiber very long time, so these steps down are just, we'd let the system go for many hours and then have to just retune the input. You can see, anyway, the transmission is fairly constant for 100 hours. If we don't do this UV treatment, then you can see this is our typical behavior of these fibers. They just die on the order of several hours, and so they become useless. So anyway, we're excited about this, and also in Andrew Wilson's poster, I'll give you a little bit of a rundown on this. It's a little bit apples and oranges, but I must say we've recently made the best fidelity gates that we ever have before, in the mid 99% range. And so we're hopeful that this will get us farther down the path. And there's also work on holocore crystal fibers by Pete Schmidt's group at PTB. And anyway, so can we get rid of the laser beams here? And very briefly, the idea is that maybe we can. So the idea here is to use rather than a laser, a state-dependent force from laser fields, is use state-dependent forces from inhomogeneous magnetic fields. So in this experiment here, which was pioneered by Christian Oswaldhaus and Ulrich Faring in our group, the idea is you put currents through here such that where the ions sit, by tuning the currents, you make the magnetic field zero, but by the positioning of these wires, you can make the gradient fairly small. And the gates work just like they would for these state-dependent optical dipole forces, but here we're using magnetic forces. And so the first experiments aren't, the fidelity of the entangled state we can create is not very exciting, but we are pursuing this. And actually, David Alcock and Daniel Schlichter are setting up a new apparatus which we think has a lot of improvements, and we'll see where we get. And so David Alcock's got a poster here at the meeting on Tuesday that describes this work. Okay. So anyway, I think you all know about our quantum logic clock here. This is, we're interested, aluminum has a nice property for an optical clock. And basically the idea is this experiment here, it's, in principle we could measure it like we do with mercury, but this wavelength is so short it's just impractical to do that. So basically what we did is when we'd drive the clock transition, we'd transfer that into the superposition of the state of magnesium, which we can measure by this Damont technique, and we make this transition through the motion superposition. Anyway, a long story. This was started by Till Rosenband and is now headed up by Dave Leibrant. But anyway, we got a few years ago, we got down to these kind of errors. The main emphasis now is we still got to get rid of the Doppler shift effects due to the residual motion, including the RF, so-called RF micromotion in these traps, and that's where the emphasis is right now. So that held the record for a while, but of course it's moving target. Just in this last year, these are the systematic uncertainties reported by Junier's group. A similar experiment in neutral atoms by Katori's group, and then most recently, this is the experiment from PTB, and so anyway, Eckhard Pike will talk about that, and Andrew Ludlow will talk about some of these neutral atom experiments. So I guess I don't want to take too much time. We have been doing other things, and some of this is highlighted here. One popular topic in the last couple of years of this idea is dissipative entanglement generation and something called xenodynamics. I'm not sure Serge will have time to talk about that, but Sebastian Glaze from the Paris lab will talk about that on Thursday. So let me conclude by saying, of course, it goes without saying almost, the work is due to lots of people over many years. This was our group picture taken just at the start of the summer here, and so all of this comes from a lot of people. You can see our group's gotten a bit bigger now. Of course, we've been lucky at NIST. We've had very good institutional support, and particularly want to acknowledge Catherine Gebian, who's been our lab director for the last 20 years. And one measure of her success is I'm the fourth person after Bill and Eric Cornell and Jan Hall to receive the prize under her directorship. So with that, I'll conclude, and here's the cast of characters again. Thanks very much.
Well, thank you, Dave, for that marvelous talk, and thank you for setting a good standard for everyone for keeping within your time. And I'm sure that all the other speakers will do that. So now we're going to take questions, and there are runners available someplace who will bring a microphone to you if you raise your hand. But while the first person is thinking about raising their hand, I will ask a question. Amazing. So Dave, you in talking about the very beginning stuff and the work you did with Hans Dehmelt and the idea that perhaps surprising at the time that a single electron was the way to go, that same kind of idea exists now with respect to, say, single ions compared to gazillions of neutral atoms. And what I'm wondering is, on the one hand, does the existence and the success of the logic clock, where there's 2 ions in the trap, although one of them is active, does this bode well for using more ions and therefore getting better statistics? And just how in general do you see that idea playing off between the single, or at the very least small number of ions, and the gazillion number of atoms, each of which have their different challenges? And
Well, this was a question from a neutral atom guy now. So I mean, one obvious penalty we paid was a single ion. The signal to noise goes down, and it is a problem for us. And I would say, I mean, we can imagine multiplexing the number of ions up, but you can see there's obvious difficulties with that. And so I there's just no question we can't think about the numbers of ions as the neutral atom guys play with, and so that is a hit. So I think you might, the signal to noise, we don't see a way to really match that. I mean, we can think about and are thinking about scaling up, but that'll always.
Yeah, but nevertheless, you're essentially the same performance. So obviously, there's something good about single ions.
Well, yeah, even in this, actually, I won't have time to go into it, but actually, one of the problems that all these optical experiments face is the phase noise of the laser oscillators. And there is a way, these great stabilities that you'll hear about that were demonstrated in the neutral atom experiments, we can actually reach the same stabilities because we can get rid of we can subtract out the laser phase noise by doing common interrogation. But there's no question that, you want more atoms or ions in our case. So I think we'll suffer from that, but we hope to be able to compete on the systematic effects, though.
Thanks. So is there a question out there, and would you stand up so I can see that you're there? Yes, here. We need a microphone over here.
Hi. What is the typical distance of the ions from the surface of the surface trap when it's trapped?
Yeah, it's about the same as the spacing. So the spacings we get in the one experiment I showed are about 30 microns, and that's also the approximate distance of the ions to the electrodes.
Okay, no, why I'm wondering is it possible that these heating effects can come from some sort of a vacuum fluctuations? Is it too close for Casimir-Polder to affect?
Well, at some level, maybe that's right. But I think right now it's pretty clear it's related to stuff on the surfaces. And even if we could make pristine surfaces, we also have to worry about the basically Johnson noise from resistance in surfaces. But I think in nearly all, certainly in all the cases we've looked at, we can do a pretty good estimate of what that noise is, and we're still above that. So it seems to be related to these surfaces effects, at least right now.
So are there other questions out there? Yes. Can you give Maciek a microphone?
Dave, so in the context of quantum simulators, you have mentioned the Ising model in the transverse field, which for short-range interaction is quite well-known model in condensed matter physics, but when you can control the decay of the interaction power load, and of course it's a very interesting model that is not, physics is not very well known, and there is a lot of interesting things to detect. But still, it's not a question of neutral atom, Guy, I promise. In atoms, however, you have a possibility of having many internal states, so going to high spin and so on. Are there any prospect of having, say, ions with 3 internal states and doing things like that? Anybody thinks about it?
I think the answer is yes. I think, we're still entering this business that is the ion guys as a whole, and so we're trying to stick with these bit simpler problems. I think one thing when you think about higher spin values, you can certainly think about hyperfine manifolds where the effective spin is a lot higher. And where the issue comes is in state readout. If you go to these higher, typically it's, we're in the case, the qubit experiments, we're able to distinguish one state from another, and it's typically much harder to distinguish states in higher spin manifolds. It's possible, but it gets more complicated. So I think so far, I think it's fair to say we haven't thought a lot about that, but people are beginning to think about these higher spin states.
So one more, if we can bring a microphone to Gerhard.
Thank you. So following in the spirit of Maciek, so what do you think is the limit about scalability in the number of single ions you can control in an ion trap in the future?
Well, I'll give the optimistic answer. There's no limit. but I don't know, Gerhard. I think we just keep going along. But I think there's reason to be optimistic. We can scale up to larger and larger numbers. And I think, as you know, there's several approaches. One of our approaches is to make arrays of traps where we move information around by moving the ions. But there's other ideas too that might be viable. So.
Well, I can't think of a better note to end on. In our kind of physics, there are no limits. Let's thank Dave again.